Hello everyone, Victor is here, your organic chemistry tutor, and in this video I've decided to do something a little bit different from what I normally do on my channel, and here I'm going to go through a practice exam from Harvard University which was administered in 2014 summer class. And while this exam is over 10 years old from the time when I'm recording this, the questions in this test are fairly representative of what you might expect at the end of the second semester of organic chemistry that will cover the entire scope of organic chemistry, starting from the very beginning of Organic Chemistry 1 all the way to the very end of Organic Chemistry 2. This exam is open to public and you can easily find it on Harvard Canvas page, so if you want to download your own copy, you can go there and find it there as well. So if we look at the front page of this exam, it says that it should take place from 8:30 in the morning to 11:30 in the morning, which is 3 hours, which is plenty of time for an exam. Name, well, I'm taking this exam with you, so I'm going to say Victor over here, and let's look at some important notes that we have given to us. It says that the exam is 18 problems on 18 pages. Well, that kind of explains why we would need 3 hours. Hopefully, we're not going to take all 3 hours here. Do not write anything in red ink. Well, hopefully, purple is okay. Now, we have our normal scoring page, we don't care about that, so let's dive right into it. And the first page here is a bunch of reactions. So for each of those reactions we need to find the ways how to accomplish these transformations, and we can use no more than 3 steps. So even though we might accomplish these transformations in more steps, if we use more than 3 steps, that's not going to be good for us. Which means that we should find the most concise, the most efficient way possible. So looking at my starting material and my product here, the first thing that I'm seeing right away is that we are starting from an alkene. So we have an alkene over here, and we are going to end up with an ether product. And the important thing here is that our ether is on the more substituted carbon of what used to be a double bond here, which means that we are going to be using one of those reactions that are going to follow Markovnikov rule. However, we have another potential problem here. If we use any reaction that's going to produce a carbocation as an intermediate, we are going to see the rearrangement because we have this carbon over here that is a quaternary carbon. So I'm going to say it's a quaternary carbon, and it is on the small ring, so if I form a carbocation in the position right next to it, that carbocation is going to rearrange. Absolutely going to rearrange. So we cannot do anything that will contain carbocations here. So if we want to add oxygen to our molecule and we want to do it Markovnikov way, and we want to avoid any kind of carbocation rearrangements, that is the recipe for the oxymercuration reaction. And the cool thing about the oxymercuration reaction is that it can give us the ether product right away. So for my reagents, if I'm going to use oxymercuration, it's going to be mercury 2+. Typically we're going to use mercury in the form of the acetate, so you might see something like mercury acetate or mercury sulfate. That part doesn't really matter. And for our nucleophile here, we are going to be using methanol because we are adding the methyl group with the oxygen, so methoxy group here, so that's gotta be methanol. Now, in order to get rid of the mercury from the intermediate that we are going to get there, we need to do the reduction part. So often the oxymercuration reaction is called oxymercuration reduction. And the second part of this reaction, the reduction part, is going to be sodium borohydride, NaBH4, and that reaction is done in basic media, so we are going to use some sort of a base, typically like a sodium hydroxide or potassium hydroxide. Something like that will work in aqueous media, of course. And we do not have a third step here, so we are going to cross out the third step because we don't need that. Could we do the synthesis in a different way? Well, we absolutely could, but we would have to do a few more steps, and that synthesis would have been a little bit longer. Probably the other way to go about that, if you didn't know that the oxymercuration can be done with alcohols, would be to do regular oxymercuration and then the Williamson ether synthesis, which altogether would have been 4 steps, which is a little bit too long for our purposes here. Now, moving on to the next reaction, we see that we have added the NH2 group to the end of our molecule over here. Now, what jumps here at me right away is that we are going to be making a primary amine here, And if we are making a primary amine, the predecessor to that is probably going to be some sort of a halide like this, where we have bromine, and via some sort of a SN2 reaction we can substitute it with a nitrogen-containing moiety. Now, to add that bromine to the alpha position of the carbonyl, well, that is a fairly simple reaction. If we are going to be adding just one bromine, that is going to be alpha bromination, which is going to be done in acidic media. So our step number 1 here is going to be Br2 in acidic media. So typically we're going to use something like acetic acid or any other acid that we want to use here. Typically the acetic acid here is going to be used both as a solvent and as the acidic catalyst. Now, we have our bromine here. Now, how exactly are we going to replace it with this NH2? If we do the direct reaction with NH3, unfortunately that's not going to work simply because we're going to have too many competing reactions. We're going to have the multiple alkylations on our nitrogen. Nitrogen can also potentially react with the carbonyl here, and it's just a recipe for a disaster. So instead of doing the direct reaction with NH3, we could do a reaction with something like an azide, N3, and then we can reduce that azide to give us the primary amine that we want. So we are going to do, let's say, something like sodium azide, NaN3 over here, and for the reduction step, we are going to do something like hydrogen on palladium. We need to make sure that we are doing this reduction in such a conditions that will not touch our carbonyl, and if we try to do something like with, let's say, lithium aluminum hydride, it will reduce our azide product as well, but in addition to that, it will reduce the carbonyl, so we don't want to lose our carbonyl. So we need to use something like hydrogen on palladium or platinum that will reduce azide but will not touch our carbonyl unless we do reaction at a very high temperature and high pressure of the hydrogen. Alright, so the next reaction that we have over here converts our alkene into a cyclopropane. This is a fairly straightforward Siemens-Smith cyclopropanation, and since our starting material was trans and our product is trans as well, we are not going to see any kind of problems with this reaction. There is no trickery with the stereochemistry, so this is a just straightforward Siemens-Smith cyclopropanation. And in order to do that one, we are going to have to use CH2I2 diodomethane, and we are going to treat that with zinc copper alloy, and usually in the presence of the ultrasound, which I will abbreviate as waves like that. And since we don't really need any other reagents or any other steps, I'm going to cross out the next two steps because, well, we don't need them. Now, moving to the next reaction over here, what I'm seeing is that we start with a 5-membered ring and we end up with an open chain containing 2 alcohols. The usual reaction that we are going to use to cut through carbon-carbon bonds is going to be the azonolysis reaction. So in order to do the azonolysis here, we need to have a double bond. So to get a double bond, we would probably have to reduce our carbonyl, do the dehydration, do the azonolysis, and then do the reduction of the corresponding aldehyde and ketone that we are going to get in this case, which is altogether 4 steps, which is a little bit too many steps. So we need to come up with a different way how we can accomplish this reaction in just 3 steps. Another way how we can potentially do this reaction is by inserting oxygen between our carbonyl and a more substituted carbon via the Baeyer-Villiger oxidation. So if the first step here we are going to use MCPBA, which is a common reagent that we know for the epoxidation reaction. However, in the case of the ketones, MCPBA can react with a ketone and form the corresponding ester. So in this Baeyer-Villiger reaction that we have here, our intermediate is going to look like that. We are going to end up with a 6-membered ring, inserting our oxygen between the carbonyl and the more substituted carbon connected to our carbonyl. The next thing that we are going to do is we can actually kill two birds with the same stone by doing the reduction with something like lithium aluminum hydride. So if I use lithium aluminum hydride here, it is going to reduce my carbonyl, and we are going to end up with O- over here, then the rest of my chain, and there will be another O- there, which is, if we count our carbons, 1, 2, 3, 4, 5, 6, and it is 1, 2, 3, 4, 5, 6. It is our target molecule. The only thing that we have left here is to protonate that. So we use some sort of H plus work up, and that is going to give us our target molecule. So step number 2 here is going to be lithium aluminum hydride, LiAlH4, and then for our acidic workup we are just going to do H3O plus, and I'm going to specify that we are going to do a workup, so that is, gentle conditions. All right. Moving on to the next page, looks like we have another page of same type of a deal where we need to find the possible reagents. So what I'm seeing in the first one, we have an alcohol, and we essentially need to get rid of this alcohol, preserving the rest of our structure. There are multiple ways how we can accomplish that. Probably the easiest way would be a radical reaction with something like tributylene hydride, but that's not a reaction that we typically cover within the scope of the sophomore organic chemistry, and I doubt that has been covered in Harvard as well. Based on my experience with those students, I usually have 1 or 2 Harvard students pretty much every single semester. So I don't recall that reaction in either chemistry 17 or 27, so probably not that. So we need to come up with other way. Well, probably the easiest way then is going to be to make a double bond and then reduce that double bond with the hydrogen. And we need to do it in a gentle way to make sure that we are not going to have any kind of carbocation rearrangement, so a simple dehydration with something like sulfuric or phosphoric acid and heat is out of question here. So instead, we can take our OH group and then we can convert that into a leaving group, do the elimination and then reduce, or potentially we can do the gentle elimination in one step. So let's say we can do something like POCl3 in pyridine. That is going to be a gentle E2 reaction that's going to give us a mixture of a product like this and another constitutional isomer here that's going to be like that. Then from here we can just gently reduce it using hydrogen on palladium again. So H2 on palladium, and for as long as we're not using high temperature or too high of a pressure of our hydrogen, the 4-membered ring is not going to be touched here, so we can do it this way. Potentially you can also convert your OH into a halogen with something like PCl3 or PBr3 and do elimination, or maybe you can convert it into a leaving group with the something like a tosylate or mesylate or triflate. Same difference, but an extra step. Alright, so in the next one, we have a 3-carbon chain turning into a bit of a monstrosity. So if I carefully look at my structure, I am willing to bet that this part of the structure came from my 3-membered chain, which means that essentially what I'm looking at is making this bond over here. Well, that is a primary amine. Hey there, Victor editing here. Well, that was of course the secondary amine, not the primary amine, so I misspoke. Back to the video. And we can easily make a primary amine like that via a reductive amination reaction, so that part is fairly easy. And in order to do the reductive amination, our predecessors should be the corresponding aldehyde, like so, and of course it's going to be aniline as our co-reagent here, so nitrogen connected to an aromatic ring like so, and we can do the reductive amination in either 2 steps by first forming the corresponding imine and reducing that, or doing that in one pot reaction using sodium cyanoborohydride. So the only question that we have left is how we are going to make this aldehyde. Well, we have starting material, which is an alcohol, which means that the first step here is going to be a simple oxidation. We can use something like PCC, or we can use Swern oxidation, or we can use Des-Martin periodinate, or you can use Collins reagent. Whatever it is you like to use doesn't matter, for as long as it's one of those reagents that stops at the formation of the aldehyde and doesn't take it all the way to the carboxylic acid. Then our step number 2 is going to be our aniline, so H2N phenyl ring, and if I want to do it as a single pot procedure, I'm going to be using sodium cyanoborohydride, NaBH3CN, and that is typically done at pH at around 5 or so, and that gives us our product right away. Okay. Moving on to my next reaction, I'm seeing that I'm adding this CH3 group, methyl group, to the alpha position of my carbonyl. So I end up making a new carbon-carbon bond right over here. Well, that is a fairly straightforward alpha substitution reaction, so the only issue here is that we need to make sure that we are making an enolate by pulling off this proton over here. There are a couple of ways how you can do it. You can either use a slow-acting strong base, such as sodium hydride, or you could use LDA in thermodynamic conditions, which means that you have to use something like 0.9 equivalents of LDA to make sure that your starting material is still present and we are still going to favor the equilibrium product, which is the more substituted enolate. Of course, within the scope of a regular course, whenever we are talking about LDA, we have this Pavlovian reflex to go after the less substituted side of our carbonyl. So if your instructor has only ever talked about the LDA making the kinetic enolate, then the second option is, not an option for you. But something like sodium hydride here will work for sure. So once we form our thermodynamic enolate, let's say we're going to use sodium hydride, then we are going to end up with the enolate looking like that, and then from there we're just going to do our alpha substitution. We can use some sort of CH3X, like let's say CH3I, electrons go down, electrons attack our methyl group, do a typical SN2 reaction, so our second step here is CH3I, and there we got it. We don't need any third step here, so I'm going to cross that one out. And the last reaction on this page adds the ester group over here, and then we are also adding an alkyl group. While the ester part here is going to be via something like Claisen condensation, so that one is going to be fairly straightforward. And if we do that first, the position between our carbonyls is going to be fairly acidic, so it will be really easy to deprotonate, and it will be fairly easy to add our alkyl group. So here our step number 1 is going to be reaction with diethyl carbonate in the basic media. So let's say we're going to use something like sodium ethoxide, so we will form enolate over here. That enolate going to attack our carbonyl, electrons go up, electrons go down, kick our ethoxide out. Then once we have that, we are going to end up with an enolate, so after that we can easily add our allyl bromide to that, and that's going to give us our final product, so we do not need any third step in this case. The enolization in between the first step and the second step is unnecessary, the extra enolization point, because the product of the Claisen condensation is always going to be an enolate unless you do any kind of acidic workup and neutralize that, so keep that in mind. Alright. Moving on to the next page, we have a slightly different thing that we need to do. Here we have the starting materials and conditions that are already given to us, and we need to find the major organic product. So if we have multiple, I guess we need to only focus on the major product here. So let's look at our first reaction. We have a alkyl halide, we have a secondary alkyl halide over here, and we are reacting it with potassium tert-butoxide. Well, we know that potassium tert-butoxide is a strong base, so it's strong base, and it also is bulky. Whether it's going to be applicable in this case or not, it's a good thing to remember. Now, since we are working with a strong bulky base, the most likely mechanism in this case is going to be an E2 mechanism, which means that we are going to be looking at the elimination reaction, and we are going to be looking for the hydrogens at the nearby position to our leaving group. Well, the leaving group in this case is obviously going to be a chlorine, so we have multiple different hydrogens which we could potentially choose from. We have this hydrogen over here, let's call it HA. We have this hydrogen over here, we'll call it HB, and I have hydrogen over here, I'll call it HC. Now, we know that when it comes to the E2 reactions, your leaving group and the hydrogen or a proton that you're trying to pull off your molecule must be antiperiplanar or trans to each other, which means that if the chlorine is looking at us, the hydrogen must be looking away from us. And the only hydrogen that is looking away from us, the only hydrogen that is on the dash is hydrogen C. So the major product in this reaction is going to be the molecule where the double bond is right over here and the CH3 group is still looking away from us. So keep that in mind, that for E2 reactions, the hydrogen and the leaving group, they always must be antiperiplanar to each other. So in this case, our terbutoxide is going to come in, tag on this proton, those electrons going to cascade around and kick our chlorine out. Now, for the next reaction here, we have a diene, a conjugated diene, and we have a reaction at H nu, which implies that we are going to be doing a photochemical reaction of some sort. Now, not every school going to cover the pericyclic reactions, and especially the photochemical pericyclic reaction, but if you guys have covered that, you know that for the photochemical reaction, we need to look at the LUMO orbital of our conjugated system, which becomes a new HOMO during the photochemical excitation. So if I schematically draw all of my orbitals here, I'm going to have a situation like that, where I have my 1, 2, 3, and 4 pi orbitals. I have 4 electrons on my pi system, so I have 2 electrons over here, 2 electrons over here, so that is my normal HOMO. During the photochemical excitation, one of the electrons is going to be promoted to the higher orbital, so now my new HOMO, let's say this one is going to be HOMO star, is going to be that orbital. This orbital has 2 nodes, which means that when we are closing the system up, the closure is going to be dis-rotatory. So in other words, if I were to draw this picture with my orbitals, I have the conjugated system somewhere in the background. I have my 2 edge orbitals, and those edge orbitals are in the same phase like that. So in order to close that up, this orbital has to rotate in this direction. This orbital would have to rotate in that direction. And since they are rotating in opposite direction, that is what we call a dis-rotatory closure. Which means that in this case, if I were to take my conjugated system and draw that in the way how it's going to be closing, so I have one methyl group looking like this, another methyl group looking like that, and if I'm doing a dis-rotatory closure, then what essentially I have is, so these are my edge atoms, that's the rest of the chain. I have one methyl group looking here, another methyl group looking here, and if one atom is rotating in one direction and another atom is essentially closing in the opposite direction like that, what I'm going to end up is a new bond between those atoms. Then I have the rest of my chain in the background. Then one methyl group is going to be looking up, while the other methyl group is going to looking down, which means that my final product here is going to look like this, with one methyl group looking up and another methyl group looking down, plus of course the corresponding enantiomer, depending on which direction we are going to be rotating it overall. As I said, the electrocyclic reactions like that are covered in some classes, so if you guys haven't seen something like that in your class, well, don't worry, it means that you're not going to see that on the final exam, which makes your life a little bit easier. Alright, so moving on to the next one, looks like we have a long chain with two esters, and we are first working in basic conditions. Whenever we are subjecting an ester to a basic condition, that is likely going to be a Claisen, or like what we have in this case, that is going to be a Dickmann condensation. Oh, I cannot spell today, so Dickmann condensation. In the Dickmann condensation reaction, we are going to enolize the alpha position to one of our esters. In this case, it doesn't really matter which one we are going to take because the molecule is completely symmetrical. So let's say we are going to make an enolate over here, and this enolate can react with our other ester. Overall, that means that we are going to be making a 1, 2, 3, 4, 5, 6. So we are going to end up with a 6-membered ring. So after our steps 1 and 2, our intermediate here is going to be a 6-membered ring with the carbonyl, that was our carbon 6, and then we still have an ester sitting over here. So if I renumber all of my atoms again, we have our atom number 1, 2, 3, 4, 5, and 6, like that. Now, the next one is going to be the formation of the thioacetal. Here we are using this fancy dithiol, and if it was an alcohol, that would be just a regular acetal. In the case of the sulfur, that's just going to be thioacetal, so nothing particularly special. So our next intermediate here is going to be the thioacetal here, that looks like this. We have just 2 carbon bridge between our sulfurs, then I have the rest of our molecule, and finally the last step is the Rene nickel, and of course it's got to have hydrogen. I don't know why they didn't specify hydrogen there for whatever reason, probably a typo, but it is Rene nickel and the hydrogen, not nickel by itself, and that is a rather specific reaction that's going to reap that thioacetal off. So our final product is going to end up being just a 6-membered ring with an ester sitting on it like so. This reaction is rather selective towards sulfur-containing acetals and frankly other sulfur-containing compounds as well, but basically this is another alternative how you can completely reduce your carbonyl in addition to the Clemmensen reaction and Wolff-Kirchner, neither of which would work for this particular compound because this compound would not fare well in either superacidic conditions of the Clemmensen reduction, nor would it do particularly well in the case of the Wolff-Kirchner reduction because the hydrazine will, well, not work the way we want here. And moving on to the next reaction, the last reaction on this page, we first see the sodium metal in liquid ammonia, so that is going to be a partial reduction of our alkyne, which is going to specifically give us a trans alkene, like that. And after that we have the hydroxyhalogenation reaction, where we are going to add chlorine to one atom of our what used to be double bond and OH group to another one. The important thing here to keep in mind is that this reaction is stereospecific and the chlorine and the OH groups are going to end up looking in opposite direction. This reaction is a strict anti-addition. So for our final product, we are going to say that one of those groups, chlorine, let's say, is looking at us, and then OH is looking away from us, and of course here we are going to end up with that plus the corresponding enantiomer. Now, moving on to the next page, what we have here is the opposite situation in which we have the product, we have the reagents, and we need to come up with the starting material here, which is probably one of the most complicated type of a question that you guys can face on your exam, but that is definitely something that you can see on your exam, so be prepared for questions like that. Now, whenever you are seeing something fancy for your product, or when your product is given to you in some sort of a fancy conformation, like let's say in a chair conformation or a Newman projection like what we have over here, it is always the best idea to convert your molecule into a dash and wedge notation to make sure that it is easier to comprehend what exactly is going on there. So in order to do that, what I'm going to say is I will say that this part over here is going to be my plane of paper. This will be a little bit easier for me to draw that. So then I will have my front and back atom. On the front atom, I have a methyl group looking down. I have a chlorine that's going to be on the wedge. So this part is going to be my wedges, and this part is going to be my dashes. So chlorine is on the wedge, and then on the back atom, I have the phenyl group in the plane of paper. I have chlorine that is also on the wedge, and I have a methyl group that is going to be on the dash. Now, what I'm seeing here is that both of my chlorines are looking in the same direction. However, when I'm looking at my reagents, I'm seeing that this is a simple chlorination reaction, and I know that the chlorination is a strict anti-addition, which means that the product that I have on this reaction is just a possible confirmation of my final product. And in order to predict what the starting material looks like, I would want to draw the confirmation of my final product the way it would look immediately after the reaction, with my chlorines looking in the opposite directions. And in order to do so, what I'm going to do, I will keep the right side of the molecule just as is, and I'm going to do the rotation around the middle bond and rotate the left part of my molecule. So when I'm done with this rotation, what I'm going to end up with is a molecule where now my chlorines are in fact looking in the opposite directions, which means that my starting material looks like this. I have the phenyl group over here and my CH3, my methyl groups, they are trans to each other. If you were to put the CH3 groups cis to each other for your starting material, that would have given you the wrong starting material, because that would end up being the wrong product at the end. So when it comes to questions like that, stereochemistry of the final product can be a little bit treacherous, because we can easily change the conformation of the final product, so don't get caught by that. Moving to my next reaction here, I'm seeing the azonolysis here. And importantly, in this azonolysis, I'm seeing that this reaction has the oxidative workup with the hydrogen peroxide, which means that if I were to make any aldehydes, instead of aldehydes, I would make carboxylic acids. So this OH came to us from that oxidative workup. So that means that in my starting material, I had a double bond between this carbon, and my OH group that I have over here, that OH group wasn't there. So I'm going to basically ignore that OH group altogether and pretend that this is just a hydrogen for the purposes of putting this molecule back together. So since I had a double bond between those two highlighted carbons, that means that the starting material here was just that thing like that. And during our azonolysis, we cut through our double bond, and this hydrogen that I have over here, this guy became the OH during that azonolysis reaction. But if, let's say, my second step here wasn't the hydrogen peroxide, but it was, let's say, dimethyl sulfide, your DMS, or zinc and acid, something like that, if it was a reductive azonolysis, then instead of OH, we would have ended up with the hydrogen and would have been acetaldehyde instead of the acid. Alright, so the next reaction that we have over here, we have the imine as our product, and I have quite a few different steps over here. So the very last step that I have here, the reaction with the CH3NH2 with the methylamine at pH 5, that is the formation of the imine, which means that the predecessor here used to be an aldehyde that looked like this, and I've made that aldehyde via the reaction with the dibal and the acidic workup some sort. We know that the dibal reagent, diisobutyl aluminum hydride, that is a rather specific reducing reagent. It looks like this. So we have our aluminum over here, and we have the hydrogen connected to it, and we have two isobutyl groups. That reagent is specifically used for partial reduction, among any other things, and we can do partial reduction of either acid chlorides or esters as our starting material, both going to give us an aldehyde. So for our starting material here, we could have had an acid chloride, or acyl chloride if you like it to call it this way, looking like this, or we could have some sort of ester. Let's say we could have, I don't know, the ethyl ester or something like that. That would give us an aldehyde in the first step, well, first two steps, and then we are going to do the formation of the imine, giving us the final product. And the last reaction on this page, for this one, we see that we are doing the BH3THF followed by the hydrogen peroxide in basic media. That is the hydroboration oxidation reaction, which, as we know, a syn addition of the hydrogen and the OH group to the alkene, and the OH group is going to be on the less substituted carbon. So this OH over here is going to be on the less substituted carbon out of two possible ones, so it's definitely not this guy, because this is a secondary position and this is a secondary position, so that means that our double bond used to be over here. And one thing that we are not seeing right now is that this hydrogen, the implicit hydrogen that is looking at us, which means that we do not need to move this molecule around, we don't need to change the conformation in any way or form, we just have the OH and the hydrogen, which are both on the wedges. They're already looking in the correct direction towards each other, so to speak. So that means that our starting material was just an alkene over here, like that. If we had an alkene in the other position over here, we wouldn't have such regioselectivity, simply because we have two secondary positions, while in the other case, the one on the left, we have a tertiary position, so our OH is going to definitely end up on the less substituted carbon this way. Alright, so for the next one, looks like we are looking at some more fun stuff. So consider the following reaction sequence: azenolysis of an alkene followed by the reductive workup. So we have a simple alkene, we are doing the azenolysis that forms the initial primary ozonide or molozonide, and then after the rearrangement, we are going to get the secondary ozonide or just a regular ozonide, and then finally we have a reduction over here that's going to give us our aldehyde as a product plus DMSO as the co-product in this reaction. Okay, cool. We've got that part. So draw a complete Lewis structure of ozone showing all formal charges and lone pairs. Okay, let's do that part. So ozone looks the following. We have oxygen, oxygen, and another oxygen. There will be 2 electron pairs on the first one, 1 on the middle one, 3 electron pairs on the last one, and we are going to have a formal plus here and formal minus on this oxygen. And of course, due to the resonance, we are going to have 2 possible resonance forms, where we can show this one or we can show another one with a double bond on the right side with all of our electron pairs like that, with the formal plus still on the middle guy and the formal negative is on the left oxygen. Okay, then draw out all the pi molecular orbitals of ozone, clearly indicating which is the HOMO and which is the LUMO. Okay, so for our pi system, we are going to be seeing the following picture here. We have the p orbital on one oxygen, second oxygen, and the third oxygen. We are going to have 1 electron for each of our oxygens over here in the pi bond, and we are going to have an electron pair contributing from the third oxygen. So overall, we are going to see the molecular orbital diagram with 3 molecular orbitals and 4 electrons. So if we draw it all out, so we are going to start with the molecular orbital where I'm going to show all 3 of them, and since we have 3 molecular orbitals altogether, I'm going to triplicate them. So the very bottom molecular orbital is going to have all of our p orbitals in phase, so I'm going to show all of them like that. We have 0 nodes there, and that orbital has 2 electrons. The next one will have 1 node cutting our orbital right in the middle, so we can basically pretend like that middle orbital over there doesn't even exist. Since we have 1 node, I'm going to shade one end over here and another end over there like that. That orbital also have 2 electrons. And then the final one, we are going to have 2 nodes there, and I'm going to shade this one this one, and that one. So since we only have 4 electrons on our system, the very last orbital here is not going to have any electrons. So by the definition, the last orbital that does have electrons is going to be the HOMO orbital. So this is my highest occupied molecular orbital over here. And the very next orbital without any electrons, that one is going to be our LUMO orbital. So that one is our lowest unoccupied molecular orbital, like that. Alright, moving on to the next part over here. So your classmate suggests that ozone would react with dienes in a similar cycloaddition way as shown below. Provide a complete curved arrow mechanism for this proposed reaction. Well, if we want to provide a curved mechanism for this reaction, I would probably start with the oxygen with a negative charge. Those electrons go here, which causes a cascade of the electron density like that. So overall we are going to end up making a bond here, here, and electrons move onto our double bond like that. Using a frontier molecular orbital argument, briefly explain why the reaction shown in this part, so in part B, would not be expected to proceed as shown. Well, in order for our reaction to happen, we need to have the HOMO orbital of one species matching with the LUMO orbital of the other species. We already have a HOMO-LUMO orbital diagrams for the ozone, so what I'm going to do, I'm actually just going to take this part over here, duplicate that, and let's just drag it over here, so we have that for easy reference. And we also have the reaction with butadiene, so butadiene over here. So in order to draw the HOMO-LUMO orbitals for the butadiene, I'm not going to draw all of them, I'm just going to draw the HOMO and the LUMO for the butadiene. Butadiene also has 4 electrons in the conjugated system, which means that the HOMO orbital there is going to be the one with the single node, so the HOMO orbital with the butadiene is going to be the one where I would draw it like this, and I would put one node in the middle, electrons over here. We are going to have 2 electrons in this HOMO orbital. I'm going to show that as a HOMO, and the LUMO orbital here is obviously going to be the very next one with 2 nodes, so the LUMO orbital for our butadiene is going to look something like this, where I have 2 nodes. Let's say these are my 2 nodes. I have shade, 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 and that one already has no electrons on that, so that is our LUMO orbital. So in order for this cycloaddition to happen, the HOMO orbital needs to match the LUMO orbital of the other molecule. Well, in this case, if I compare my orbitals, this HOMO over here does not match the LUMO on the other molecule. Likewise, the LUMO orbital that I have for my butadiene does not match the HOMO orbital that I have for my ozone. So no matter how I try to match those 2 molecules, the ends of my orbitals, they do not match appropriately. So instead of a productive overlap between those orbitals, we are going to have an unconstructive or non-bonding overlap, which not going to make the cycloaddition happen. So in order for the cycloaddition to happen, we somehow need to match those ends, but it doesn't seem like matching in this case, so it's simply not going to work. Alright, so moving on to the next page, we have another ozenolysis question. So again, we have all the same steps. We have formation of our ozonide, then we have the formation of our final product. Cool. So in the rearrangement step in the ozonide, we need to show our curved arrows for all of these transformations. Well, if we look very closely at which bonds are being made and which bonds are being broken in this case, we can see that we would need to move our electrons in sort of like this fashion over here. This goes here, that goes here, and then the electron pair from our oxygen goes over here. So we are going to end up breaking a bond between the carbons, breaking a bond between the oxygens, making a new bond between carbon and oxygen on the bottom, and also making a new carbon-oxygen bond on top over there as well. Then, once we rotate those guys in space, we are going to do the essentially cycloaddition step where these electrons go here, those electrons go here, and these electrons go onto the oxygen. So in this case, we end up making a new bond between carbon and oxygen. We end up making a new bond between this carbon and oxygen, and this oxygen over here becomes neutral. And I do have a dedicated video on the ozonolysis of alkenes, so if you guys want a little bit of a refresher on that, you can definitely check it out, where I go step by step with all of those electron movements. But for now, moving to our next question, what we are seeing here that we need to identify the LUMO of the ozonide and the HOMO of the dimethyl sulfide in the reduction part, and we need to draw the complete curved arrow mechanism for the reduction part of the ozonide. Well, probably it's going to be easier to start with the mechanism first and then to identify our corresponding participating orbitals. So here, if I were to redraw my ozonide, it's going to look something like this, and when I reacted with dimethyl sulfide, which looks like this, what's going to happen here is sulfur is going to attack one of these oxygens, breaking an oxygen-oxygen bond. As a result of this nucleophilic attack, we are going to end up with O- over here, oxygen, then we have another oxygen over here, and that oxygen is now connected to sulfur, which in turn is connected to two methyl groups, and we have a plus charge on the sulfur. Then from here, the next step, we are going to essentially break our molecule into two pieces. When we are going to break this carbon-oxygen bond, and that essentially gives us one carbonyl as our final product, and another intermediate. We have this O- here, then O and sulfur with a couple of methyl groups. And the last bit here is that the oxygen is going to kick our leaving group out, which going to give us another equivalent of our final product and an equivalent of DMSO, which we can write like, oops, that's supposed to be a negative charge, of course, so we can write it like this, or we can write it with the sulfur-oxygen double bond if you really want to. Now, looking at this reaction very carefully, we can see that the reaction starts by taking electrons from the sulfur atom. Those are non-bonding electrons, so the HOMO on the sulfur that is going to be participating in this reaction is going to be non-bonding electrons on the sulfur atom. Now, the LUMO here, what is accepting those electrons is the anti-bond, sigma anti-bond on the oxygen, so it's the oxygen-oxygen, essentially a sigma star between those oxygens that's accepting those electrons, so that is going to be our LUMO orbital, lowest unoccupied molecular orbital, which accepts those electrons. And there is a horrible star, so let me fix that star. There we go, sigma star. When it comes to identifying your HOMO and LUMO interactions and any kind of reactions, it is always a good idea to draw the mechanism first and then see where exactly the electrons are going. That will make your life significantly easier. Alright, so moving on to the next reaction, next page, next question here, we see the question where, so we have a reaction here upon treatment with nitrosonium cation compound A, so here is our compound A, is transformed into compound B, okay, here is the compound B, via the diazonium intermediate shown below, so this is our diazonium intermediate. Okay, awesome. Circle all of the stereogenic carbons in compound A and label each with the correct R or S designation. Okay, well, so we have two stereocenters here. We have this one, I will mark it with green, and we have this one, I will mark it with red. So if I wanted to show my R and S stereo descriptors here, let's make it a little bit bigger. Sulfur is going to have the first priority for the green one, then it's going to be the one with the nitrogen, then we have our carbon over here, and Finally, we have implicit hydrogen. That guy is going to be number 4. Conveniently for us, that hydrogen is already looking away. So in this case, we are going counterclockwise, and counterclockwise means the S stereo descriptor. Now, moving on to the one in red, for that guy, I have the first priority being my nitrogen. The second priority here is going to be sulfur. Well, not the sulfur itself, but the carbon connected to sulfur. The third priority is going to be the carbon with the oxygens. And the last lowest priority is going to be my hydrogen over here. So that is going to be priority number 4. Now, in this case, my lowest priority does not look at me, so what I need to do, I will redraw my stereocenter just as is, but I will forget about the actual groups and just show the priorities. I have 1, 4, 2, and 3. And what I'm going to do here to make sure that my lowest priority, my number 4, is looking away from me, I'm going to do my favorite trick, which I call a double flip, where I'm going to flip the positions of 1 and 4 and 2 and 3. If I do so, that's going to give me the same stereocenter, but now 1 is here, 4 is here, 3 is here, and 2 is there. And we can see that in this case we are moving counterclockwise, so that is the S stereocenter as well. So both of our stereocenters are S stereocenters. Alright, so the next part here, we need to draw a curved arrow mechanism to account for both steps and the transformation of compound A into compound B, and your mechanism must account for the observed stereochemistry to get full credit. Okay, well, let's dig into that one. To make my life a little bit easier, well, first of all, let's redraw our starting material here. And the starting material is going to have methyl group, we have sulfur, we have CH3 over here, then I have my nitrogen NH2, and I have my CO2H, like so. So to make my life a little bit easier for right now, especially for the first step, I'm going to designate this part of the molecule as some sort of an R. So that will be the same thing as, for right now, saying that I have R NH2. And I'm not going to look at the stereochemistry for the moment because the diazotation reaction, the formation of that diazonium intermediate, is not going to change the stereochemistry, so I'm not going to be dragging my dashes and wedges with me throughout this reaction. They're just going to make picture extremely cluttered. So the reaction starts by doing the reaction with our nitrosonium cation, where we have nitrogen-oxygen triple bond with a formal charge on the oxygen like so. Step number 1 here is going to be the nucleophilic attack from nitrogen onto the nitrogen like so, moving the electrons onto the oxygen, which going to end up giving me the intermediate where I have N, H once, H twice, and I have my NO like that. And of course we're going to have a plus charge on my nitrogen over here. Then from here we're going to have a couple of proton transfers. One proton transfer is going to pull my proton off the nitrogen, so let's say I'm going to bring water as my base here, and that water is going to pull that proton off, and the other step is going to take my freshly protonated water in the form of the oxonium ion over here and protonate my oxygen of my NO like that. So I'm going to combine both of those steps together. That going to give me an intermediate where I have now NH connected to N double bond O with the hydrogen and of course the formal plus charge. This one has a bunch of resonance structures, one of which going to move electrons all the way from one nitrogen essentially to our oxygen via the middle nitrogen. So if I were to draw that resonance structure, I would end up with something of this sort. I have H here, double bond N, and I have OH like that. So these are my resonance structures, and of course I have a plus charge on this nitrogen over here. Now from there I am again going to have a couple of proton transfers. I'm going to pull the proton of this nitrogen, and I'm going to protonate my OH group. So I'm going to do the same trick as I did last time when I'm going to show a water molecule coming in and deprotonating the nitrogen, and the H3O plus coming in and protonating my oxygen. So I am again combining two steps in one, which going to end up giving me the following. I have my R group here, I have N, double bond N, then I have H2O plus over here, which is an excellent leaving group. And what do leaving groups do? Well, they leave. So we are going to have the assisted ionization here, where this nitrogen is going to help push our water out, and that going to give us the intermediate looking like so. So we have our R, we have nitrogen, triple bond, nitrogen plus over here. Now, if I expand what my R used to be, I'm going to show the rest of my molecule completely. So I have my methyl group, sulfur, methyl group up here, then this N, triple bond N with a plus on the nitrogen, and then I have my CO2H, my carboxylic acid, like that. Now, the next interesting thing is that we are going to go from this diazonium intermediate, and we are going to end up with our compound B. But here is the trickery. We have the stereoconfiguration of the diazonium intermediate essentially being the same as the stereoconfiguration of our compound B. If that was a simple SN2 style reaction, well, we would expect to see the change in our stereoconfiguration. We would see the inversion of the stereoconfiguration. If we expect something like an SN1 reaction, well, first of all, we would be rather unfortunate to form a carbocation next to an electron withdrawing group like the carboxylic acid, so that would be extremely unstable. And if we were to see something like that, that carbocation would instantly rearrange. So it doesn't look like we have either SN1 or SN2 reaction here. So what exactly do we have here? And this one is actually rather tricky, because unless you have seen something like that, that would be really difficult to figure out what's going on there. The effect that we are going to see here is referred to as enchimeric assistance. So what happens here is that this sulfur, being an excellent nucleophile, can essentially react intramolecularly, doing the SN2 substitution like so, making a three-membered ring intermediate that will look like this. So I have my sulfur over here with a methyl group. That sulfur is now going to be on the wedge, because this is an SN2 style reaction. I have my carboxylic acid over here, and of course I still have the methyl group that used to be there to begin with, and now we have the plus charge on this sulfur. And as I've mentioned, this type of effect is commonly referred to either enchimeric assistance or neighboring group participation. So from this point, we are going to bring our water, H2O, and we are going to do another SN2 style attack here, where our oxygen is attacking here, opening our sulfonium ion, giving us the intermediate where sulfur is back where it belongs on the left side of our molecule. We still have our carboxylic acid over here, but now I have my oxygen again looking in the back with a plus. And of course, once we do our proton transfer, so I'm going to bring another water molecule over here, pull that extra proton off, and we are going to end up with our final product. For the sake of time, I'm going to cheat a little bit, duplicate my molecule over here, and get rid of my plus charge, and just redraw that as an OH like that, and that's our mechanism. So the formation of the diazonium intermediate, the diazotation reaction, is probably something that you have seen in your course. This is a fairly standard reaction, and we do talk about that when we are talking about the diazonium salts in the second semester of organic chemistry. So that part probably wasn't something new. The enchimeric assistance or the neighboring group participation, where this sulfur joins into the mechanism and makes a three-membered ring intermediate, that is probably something new. From the top of my head, I can only name one, maybe two textbooks that even look into that, Loudon being one of those textbooks, and in the summer of 2014, where this exam is coming from, I believe Harvard used Loudon, so that would explain why they know this part of the mechanism, because I don't recall this being in textbooks currently in most any other textbooks. So if something like that comes on the exam, well, your instructor is trying to be awfully cute, and now you will know how to deal with something like that. So when you have a sulfur or any other large element, usually it's sulfur or phosphorus, they can potentially make three-membered ring intermediates like that and help the reaction by also messing up a little bit of your stereochemistry in the way here. Alright, so moving to the next page, oh, looks like we have some spectroscopy here. Cool, so you have just synthesized a new compound, yay me! And the following spectroscopic data are obtained. From the mass spectrum you have deduced that the molecular formula is C4H7 ClO2. Well, since we are dealing with spectroscopy here, the very first thing that I want to do is to calculate my hydrogen deficiency index or degree of unsaturation here. I'm going to remind you real quick that that one is calculated by taking twice the number of carbons plus 2 minus hydrogens minus halogens. We ignore oxygens, we plus any nitrogens that we might have here, and we are going to divide that by 2. The utility of the hydrogen deficiency index is that each degree of unsaturation corresponds to either a cycle or a double bond, which makes it a little bit easier to see what type of moieties we expect to see in our molecule. So in this case, if I wanted to calculate my hydrogen deficiency index, I would have twice the number of carbons, which is 4, plus 2 minus 7 hydrogens minus 1 halogen divided by 2, so that gives me 10 minus 8, 2 over 2, that gives me 1, which means that in this molecule I'm going to either expect a double bond or a cycle. Now, looking at my infrared spectrum, we have the next question that says, from the infrared spectrum, circle the functional groups that are definitely present. Well, what I see here is this peak at around 1750-ish or so that definitely screams the presence of the carbonyl at me, and that is 1 hour degree of unsaturation, so we know that in addition to our carbonyl, we are not going to be seeing any other cycles or any other double bonds. So from the infrared spectrum, circle the functional groups that are definitely absent, while in this case we definitely are not seeing the OH, because OH would have been a nice broad signal over here, and we are not seeing that. We are not seeing a carbon-carbon double bond, because that one usually shows up at around 1650, and we are not seeing that. And finally, we are not seeing a nitrile here, because nitriles show up at around 22-2300, so those guys would pop up around this region of the IR, and we are not seeing any of that either, so none of that stuff. Then we have the proton NMR spectrum in this molecule, so we have 3 hydrogen singlet, 3 hydrogen doublet on the right, and looks like a quartet 1 hydrogen over here. So I will remind myself that molecular formula here is C4H7ClO2, and I know that I have a carbonyl in this molecule, so that it's a little bit easier for me to distinguish between the different peaks potentially. So this peak at around 0, that is our tetramethylsilane. This is just a standard, so we don't need to pay any attention to that one. Now, 3 hydrogens, that is most likely going to be a CH3 group. Since this is a doublet, that CH3 group, I'm going to put that into a box, is most likely going to be sitting next to one neighbor. The next one, we again have 3 hydrogens, which is again likely to be a CH3 group, but in this case, unlike the last one, we should not see any neighbors next to that CH3, because this CH3 is just a singlet. Also, based on the location of where it is in the spectrum, that CH3 is most likely next to some sort of electron withdrawing group. And then the last one hydrogen that we have over here, that is a quartet, so that is most likely going to be a CH group that is next to CH3, and we already have that fragment in our molecule that we have identified previously. So the fragments that I have in my molecule are going to be the following. I have a chlorine, I have, by the look of it, some sort of an ester, because our IR show us the carbonyl at around 1750. Then I have a CH3 group, and then I have this CH3 like that. So there are a couple of ways how we can potentially combine this molecule together. One way would be to put it together like so. We have CH3O, then CO, CHCl over here, and CH3, versus the other way where I essentially flip-flop those. So I would have CH3, CHCl, oxygen here, then my carbonyl, and CH3 like that. So in order to distinguish between these two possible molecules, what I would have to do, I would have to compare my ppm values in the spectrum and see which one is more likely. So for instance, this CH3 over here, which is going to be our singlet, that should be at around 2.5 ppm or so, but what we are seeing here is next to 4 ppm. So that already doesn't fit our spectrum, which means the second molecule that I drew here is not likely here. The other one, we have one hydrogen over here, which is going to be between the carbonyl and the chlorine, and our CH3 that is next to an oxygen, which is also an electron withdrawing group, so that fits our positioning ppm wise, which means that the molecule on the left, the one that I drew first, that is going to be my actual molecule for this spectroscopic data. Alright, moving on, looks like we have another spectroscopy question in front of us. Now we have our molecular formula C10H14O, so I'm going to go ahead and calculate my hydrogen deficiency index right away there. So I have twice the number of carbons, which is 10, plus 2 minus 14 hydrogens. I don't have any nitrogens or halogens in here, so nothing to add or subtract on top of that, divided by 2, and that gives me 4 degrees of unsaturation here. So when we have 4 degrees of unsaturation, most likely we are going to be looking at the aromatic ring here. So let's see if we have any confirmation for that and other spectroscopic information. So looking at my IR spectrum over here, the first thing that I'm going to pay attention to is that looking below 1500 is usually not going to be informative to us. So the region below 1500 reciprocal centimeters, that is our fingerprint region, and we don't usually look at that. However, we seem to have this signal over here at roughly 1600 reciprocal centimeters, so that is going to be an aromatic carbon-carbon double bond. So I will show it with a sort of like a partial bond like that. Then we have some sort of a little blip over here, probably not particularly informative, so I'm not going to pay too much attention to that. Then, looking at my 3000 region over here, I see that on the right side over here I have my regular sp3 hybridized carbon hydrogen stretches, and what looks like on the left something like an OH group most likely. And also we have some signals over here just to the right from our 3000 stretch, which is going to be sp2 hybridized carbon hydrogen stretches over there. So looking at our box where we want to identify the groups that are definitely present and that are definitely not present here, it does look like we have an OH and we have an aromatic double bond, so I'm going to show that. And the groups that we definitely do not have, doesn't look like we have a carbonyl because our double bond is a little bit too low to be a carbonyl, it's not 1700, and it also doesn't look like we have a nitrile because we don't see anything at 2300 region, so that region right over here is completely empty. Now, looking at our spectrum over here, we have a few interesting things that I'm noticing right away. One is this hydrogen over here, which is a very broad singlet. That is a dead giveaway of an OH group of some sort. Then I have 9 hydrogens, which is a singlet, which is another dead giveaway for a third butyl group. So that's going to be CH3, CH3, and another CH3 like that. Then finally, we have 2 hydrogens and 2 hydrogens in the aromatic region. We have doublet number 1, we have doublet number 2. So that is the most typical substitution pattern for the or para-substituted aromatic ring like that, where we have 2 hydrogens. Due to the symmetry, they are the same on the other side of our molecule, and you're going to have a doublet here and a doublet here. So what we know so far is that we have our aromatic ring, which counts for 6 carbons. We have the third butyl group, that is another 4 carbons, and we have OH. I remind you that our molecular formula is C10H14. 6 carbons for the aromatic ring, 4 carbons for the third butyl accounts for all carbons in our molecule, plus 1 oxygen for the OH, so we know all the bits and pieces, which means that our molecule is going to be an aromatic ring over here with the OH group on one end, and we are going to have a third butyl on the other hand, like that. Alright, so moving on to the next page. Okay, so here looks like we have a mechanism question. Provide a complete curved arrow mechanism for the following transformation, a variant of the classic Beckmann rearrangement. Well, Beckmann rearrangement, if you guys are not familiar with that one, is typically done in acidic conditions when we are going to be protonating this OH group, converting that into a good leaving group, and then from there magic happens. In this case, we don't have acidic conditions, but instead we have tosyl chloride in the presence of pyridine, and looks like we have aqueous conditions here. So we are still going to be converting our OH into a good leaving group, but with a slightly different way. So to start off here, I'm going to have the nucleophilic attack from my oxygen on my tosyl chloride, so I'm going to show the tosyl chloride being attacked and chlorine is being kicked out, so that is going to give me the intermediate that's going to look like this. I have my aromatic ring over here, I've got my nitrogen, oxygen, hydrogen on that, and then I have my tosylate, and I will represent the aromatic moiety on my tosylate as the aryl like that, and of course we have a plus charge on our oxygen over here. Then from here we can say that our pyridine or water, pyridine is more likely because it's more basic, going to come in and deprotonate that, giving us our neutral intermediate. So I have the phenyl ring, I've got my nitrogen over here, O, SO2, aryl over here like that, and the methyl group over there. Then the next thing that we are going to have here is we are going to have our leaving group dissociation, and at the same time we are going to have one of our carbon bond migrating. In the Beckmann rearrangement, typically the more substituted group is going to migrate, so we are going to be looking at the migration of the group on the left over here. So as my leaving group dissociates, we are going to have this one migrating onto the nitrogen, which essentially going to give us a rather interesting situation. We are going to make a new bond between nitrogen and the carbon, break a bond over here, and break a bond to our leaving group. So what that going to give us is the following carbocationic species. We have the phenyl ring, we have this connected to nitrogen, double bond here, another carbon, and we have a plus charge over here. And of course we can show that this part is stabilized by resonance, so I can draw the resonance structure here, where my phenyl ring is connected to nitrogen. Now that's a triple bond, like so, and we have a plus charge on the nitrogen like that. So from this point we're going to have a nucleophilic attack by water, so I'm going to show my water molecule H2O that is going to be attacking my carbocation, which going to give me the next intermediate. Let's write it over here. I have the phenyl group, I have the nitrogen over here, bond, bond, O, H, H, plus on my water like that. From here we are going to have a proton transfer to get rid of the plus on our water. So I'll use another equivalent of water to come in as a base, or maybe I can use pyridine, doesn't really matter what we use here. Come in, pulls that thing off, giving me my next intermediate that's going to look like this. I have nitrogen, double bond here with an OH group like that. So this species really resembles something like an enol, so we are going to have a process very similar to keto-enol tautomerization, where the newly protonated water that we have just formed in the previous step can come in and protonate our double bond like so, giving us, we have phenyl ring over here, we have nitrogen with the hydrogen, and we have CO double bond with the plus on the oxygen like that. And of course we have plenty of resonance structures. For that one I'm not going to draw all of them for the sake of time, but the last point here, the last piece of this mechanism is going to take another equivalent of our water or pyridine, bring that in, pull the proton off, and that is going to end up giving me my final product, that is my amide, like so. So this is a rather interesting mechanism. Let's put it all on the screen like so. I need it a little bit more like this. Yeah, so as I said, this is a rather interesting mechanism, and I suspect they have talked about this mechanism sometime during the course. However, this is not the type of a reaction that we normally would expect in the sophomore organic chemistry. So if you guys haven't seen something like that, if your instructor is particularly creative, your instructor might show you something like that on the final exam. However, I wouldn't expect a reaction like this, or any type of a reaction that you haven't seen in your course just randomly pop up on the exam. Usually whenever you have some sort of fancy reaction showing up on the exam, it is going to be a slightly different version of something that you have already seen before, so something like that would probably only show up if you have already seen something of that sort before. And so moving to the next question, here we have another mechanism question. So the following transformation occurs when the dichloroether below is treated with benzene and aluminum trichloride. So that looks like a some sort of a Friedel-Crafts style reaction. Provide the curved arrow mechanism to account for the formation of the compound X here. So since this is going to be a more or less typical Friedel-Crafts reaction, we are going to say that our aluminum chloride is going to make a complex with our ether that is given to us, giving us an intermediate that looks like this. So I have O-methyl here, I have Cl once, Cl twice, and the Cl on the right side is now bound to my aluminum chloride with a formal plus here and formal minus on the aluminum. Next, we are going to have our leaving group dissociation, so this thing is going to pop off, giving us a carbocationic intermediate, so we'll have Cl, O, CH3 with a plus on the oxygen like that. Then we are going to bring in our aromatic ring and do our normal Friedel-Crafts style reaction where the aromatic ring reacts with our carbocationic intermediate. That going to give us the corresponding cationic resonance stabilized intermediate like that, and we are going to pull the proton off and reform our aromatic species. So I'm going to use aluminum chloride here to pull the proton off, just like we would normally do for any kind of Friedel-Crafts alkylation reaction, and we get our final product over there. Alright, so the next part of this reaction here says that the compound X rapidly reacts with water in an SN1 type reaction as shown below. Provide a curved arrow mechanism for the reaction compound X to give the product shown, and be sure that your mechanism is illustrated is SN1 and explanation of why it goes so rapidly. Okay, well, if it is an SN1 style reaction, it means that we are going to start with the leaving group dissociation. Out of two possible leaving groups that we have in front of us, the most likely leaving group is going to be chlorine. So we are going to say that chlorine is going to pop off first, and we are going to end up making a carbocationic intermediate that will look like this. So we have O-methyl group here with a plus on our carbon. Now, the reason why it happens so easily is because we have a ton of resonance structures here. We can use our oxygen to provide electron density, or we can use the aromatic ring to provide the electron density. This is not just a benzylic position, but that is a benzylic position with the heteroatom, which means that that carbocation is incredibly stabilized by the resonance. So because of that, it will form extremely easily. But now, as we have our carbocation, the next thing that we can do here is the attack by water, the nucleophilic attack over here, which is going to give us an intermediate looking like this. So we have the aromatic ring, we have O-methyl over here, and then we have OH, H, and plus like that. Now, if I pull the proton off here with another equivalent of water, what I'm going to end up with, so I pull this one off, that going to give me a very familiar species that we have seen a million times throughout our course, and that would be the hemiacetal. And we know that hemiacetals are not particularly stable, so we're just going to keep on going with this reaction that's just going to be essentially a hydrolysis of the hemiacetal that going to essentially give us the aldehyde at the end. So I'm going to grab that protonated water that I have just produced a moment ago. I will protonate my methoxy group like so, giving me the intermediate where I have methyl group here, hydrogen there, plus then I have my OH. Now my methoxy group is a leaving group, so we can push that thing out, giving us the next intermediate that's going to look like this. So we have our OH plus, and whatever we have floating around, that can be the methanol that we just kicked out or another equivalent of water, doesn't matter, going to come in, pull that proton off, and we are going to end up with our target molecule over here. So essentially, once our leaving group dissociates and we form our intermediate, which is a hemiacetal, from that point on it's a simple hemiacetal hydrolysis. Alright, so moving on to the next page, next question, looks like we have another mechanism question here. So provide a complete mechanism for the following multi-step transformation. Use the curved arrow formalism for each step. Alrighty. So the first thing that we are seeing here is that we are reacting with sodium amide, and we know that sodium amide is a very powerful base, and we have three equivalents for that strong base here, which is very relevant in this case. So step number one here is going to pull off one of these protons with our amide. So I'm going to show NH2 minus over here, coming in and doing the E2 reaction, pulling the proton off and kicking one of our bromines out. So what that going to give us will be bromine, then we have our double bond, then we have oxygen, and then we have that third butyl sitting there. Then the next equivalent, so that's our product from the previous step, the next equivalent of our NH2 minus going to come in and do that one more time. So we are going to end up with the triple bond now, and then we have oxygen here and our third butyl group like that. And then the third equivalent is going to come in and pull off the proton from our terminal alkyne. I will remind you that the pKa of the terminal alkyne is somewhere around 25, which means that the amide is definitely strong enough to pull that proton off. So that third equivalent is going to come in, pull that thing off, and we are going to end up with the negatively charged carbon at the end of our alkyne, and then the rest of our molecule like so, which is our intermediate right over here. Now, next we are reacting it with the epoxide, and then we have excess of TFA. Well, we'll get to that part. And first of all, let's look at our reaction with the epoxide. So epoxides are fairly electrophilic, and our acetylenide ion that we have just formed is rather nucleophilic. So what we are going to end up with is the nucleophilic opening of the epoxide ring, which is going to give us the new carbon-carbon bond. So we have our carbon-carbon triple bond, the rest of our molecule, the new bond that we have formed here, 1, 2, and we have O- there like that. There is nothing else that can really happen at this point, so that will be it here. So the next thing that can happen here, or the next thing that rather we are going to see here, is the excess of TFA, which is going to be the excess of our dry H+. In other words, it's just the source of H+. TFA stands for the trifluoroacetic acid, which is a very strong acid, and it's a very common source of the H+ when we need super dry conditions for whatever reason. So we are going to say that in the next step we are first of all going to be protonating our oxygen over here, that's going to end up giving us a molecule that looks like this. Now, from this point, we remember that we somehow need to perform the cyclization over here, and looks like a chunk of our molecule is going to fall off. But let's not try to do the most common mistake that I see a lot of students do. Let's not force our mechanism to give us the products regardless of what we might see here. Let's do the most logical next step. And since we are still working in acidic conditions, the next best step here is going to be to protonate our alkyne. And because our alkyne is the resonance conjugated with our oxygen, protonation of the alkyne is going to be fairly easy, giving us a new species that's going to look like that. So we have the carbon-carbon double bond. We have added our hydrogen to one of those carbons. We have double bond with this oxygen over here, which is going to be positively charged, and then we have 1, 2 carbons, and we still have the OH group over here. So we form this funky looking cationic species. Now, the next thing that we can do here is we have a very electrophilic species and we have a nucleophilic species right here in our molecule, which means that these two guys can react with each other, giving us a cyclic compound. And let's see, we have 1, 2, 3, 4, 5 carbons. So that actually does give us a 5-membered ring, and we needed to end up with a 5-membered ring. So what we're going to get here is going to be the following. We will have a 5-membered ring with an oxygen, so I'm going to redraw my carbon-carbon with the hydrogen over here. Then I'm going to bend my chain around, make a new bond with my carbon. I have the oxygen with the third butyl group still here. I have the hydrogen still attached to my oxygen. So I have my carbons 1, 2, 3, 4, and 5 still everywhere they, where they need to be. Then I have plus on my oxygen like so. So from this point, what we need to do, we need to deprotonate our oxygen. So I'm going to potentially use either the solvent that we have over here. Did we see any solvent? Well, it doesn't look like we have any solvent. So what I'm going to be using is the conjugate acid of my trifluoroacetic acid, CF 3 over here to pull that proton off. So we'll pull that guy off. That gives me the intermediate that looks like this. So I have 5-membered ring, oxygen here, then oxygen here, and third butyl group like that. And then from this point we need to get rid of the third butyl over here, and we can do so by first of all protonating our double bond. So I'm going to use my trifluoroacetic acid again. So this guy over here, the electrons from my oxygen come down, electrons go here. We are going to end up with the protonated product that looks like so. We have the O and then third butyl group like that. The hydrogen, this hydrogen that we have added to our molecule, is hiding over here right now. We used to have a hydrogen there to begin with, and I will show it here in green, and that hydrogen is still there. And the last bit here is to lose our third butyl group. We can do it just like so. That is actually a somewhat decent leaving group because the carbocation that you are going to form there is somewhat stable due to being tertiary. So we are going to have our tertiary carbocation over here. Okay, it's a little bit off the screen. Let's pull it up a little bit like that. And the last bit for us would be to pull one of these protons off. Again, we can use our trifluoroacetic acid as our conjugate base over here. So this guy comes in, pulls the proton off, and that gives us the second product here, which is an alkene that's going to fly away. So that's a rather long mechanism, but the important thing here to remember is that when you are working in acidic conditions and you have a third butyl group like this one, that third butyl group does have tendency to pop off in the form of the alkene. So that is something that you might want to keep in mind if your instructor decides to show something like that or try to be fancy and give you a reaction, a reaction of this sort. All right. Moving on to the next question, we have another curved arrow mechanism. So provide a complete curved arrow mechanism for both steps of the following transformation. Well, what a monstrosity that is. Well, let's try to figure out what's going on there. So the first thing that I'm seeing here, we have this sodium methoxide in methanol, which is a base. And I am seeing an alpha-beta unsaturated compound over here, and I'm seeing a stuff with a whole bunch of esters. So something tells me that we are probably looking at some sort of a Michael addition here, possibly like a Claisen or retroclaisen condensation, something of that sort. And another important thing that I'm seeing here is we are losing part of our molecule, so it definitely does look like a retroclaisen condensation somewhere in the middle there. So let's try to dig into that direction and see where we get with that. So in order to do the retroclaisen, we would have to start with our methoxide. I'm just going to draw it as OMe, and we're going to attack one of our esters over here, forming the corresponding tetrahedral intermediate. So I have methyl O, I have my carbonyl, then I have my O minus, O methyl, another O methyl over here, then I've got the phenyl group and another ester over here like that. Now in the retroclaisen condensation, we are going to have these electrons go back, and instead of kicking one of the methoxy groups out, we are actually going to break one of our carbon-carbon bonds. Well, in this case, what we're going to end up with is the following intermediate. I have my ester number 1, I have my ester number 2, I have my phenyl group, I've got minus right over here, and this part of the molecule over here actually turns into methyl O, CO double bond, and another O methyl. So that is this molecule. So we have found a way to make one of our products. Now, if I look at the negatively charged intermediate that I have just formed, this guy over here, well, that one is an enolate, and that is a very well resonance stabilized enolate, and we have the Michael acceptor right there in the form of our alpha beta unsaturated compound. So as soon as we form this enolate, we can react that with our Michael acceptor. So let's redraw that alpha beta unsaturated, our enon that has carbonyl over here, then ethyl group like that. So this Michael donor reacts with Michael acceptor like so, and we are going to end up with the new carbon-carbon bond between this carbon and that carbon over here. So if I carefully trace my molecules, first the one that used to have a double bond now is going to be an enolate looking like this. I've made a new carbon-carbon bond between the position over here, and that will be a carbon of my enolate. So I have my phenyl group here, I've got my ester, and I have another ester like that. Oof, that looks rough. Now, in order to get our final product, let's scroll it a little bit back up here. Looks like for our final product, we are making a new bond between these two carbons, which means that I would have to enolize this position over here, and I would have to do an intramolecular Claisen or a Diekmann condensation with one of my esters over there. So essentially I am first going to do a couple of proton transfers here. First one, I will use ethanol that I have floating around to protonate that part, and then, if you guys don't mind, I'm going to use my ethoxide to deprotonate that here like that. So I'm kind of combining two steps in one. So that will give me the enolate that I need, which would look like this. I still have my 6-membered ring. I have my O- over here. Now the double bond is on the right side. I have my phenyl here. I have my COO methyl there, and I have my other carbonyl with the methoxy group looking like that. Now, from this point, we can have these two reacting with each other. So now we are going to end up making a new bond between this atom and this atom over here. That's going to give me a new 6-membered ring. So the left side stays unchanged. On the right, I have a new carbon-carbon bond there. So I have O-, I have O methyl group, I have phenyl over here, and we have COO methyl like so. And to finish up our Diekmann condensation here, these going to kick our methoxy out. So that going to give me, I have my 6-membered ring, I have my other 6-membered ring, I've got my methyl group, I have this, I have phenyl group, and I have COO methyl like that. Now, of course, the position that we have between our carbonyls, this position over here, is fairly acidic. So the methoxide that I have just used, we are going to pull that proton off, and we are going to immediately enolize that position, which is a driving force for the Claisen or a Diekmann condensation, which is pretty much the same thing anyways. So we are going to end up with the phenyl group here. We have COO methyl there, our enolate looking like that. And the last part here, if I scroll all the way up, the last part was the acidic workup that we have here. So in order to do our acidic workup, I'm just going to bring some sort of acid, H3O+, doesn't matter where that thing is coming from, and we are going to protonate our enolate like so, giving us the final product that looks like this. So I have my phenyl group here, I have my COO methyl, I have carbonyl, I have a methyl group, and I have another carbonyl there. And there we have it. That's our final product, and we got the mechanism here. So I guess the tricky part here was to recognize that the entire reaction starts as the retroclising condensation, because while we do have the alpha-beta unsaturated compound, it doesn't really have anything to react with, so we needed to form our enolate, our nucleophile in some sort of way, and kind of a giveaway that we are going to have the retroclising here is the formation of this co-product here, which is an ester, ester of carbonic acid, and in order to make that, we had to pull it off from one of our starting materials, and the only place where we can pull it off if we pull off one of these guys in a retroclising condensation style reaction. Alright. With this mechanism in mind, let's move on to the next one. So provide a complete curved arrow mechanism for the following transformation. Please note that although thiamine is used in this transformation, this process takes place in the lab, no enzymes are involved. Well, the reason why they're saying that is because thiamines and imidazole moieties are often going to be part of the enzymatic pocket, and reactions like that typically do happen within the enzymatic pocket, but this reaction, this particular reaction, really looks like, well, doesn't only look like, but it is essentially a modification of the benzoin condensation. And funny enough, one of my very first videos that I put on YouTube channel is about the benzoin condensation. It was a long time ago. Anyways, so in this reaction, what we are going to be looking at is forming some sort of intermediate with our thiamine, and then from there doing this condensation in general. So the first thing that's going to happen here, this H that is shown here is indicated for a reason, because the first thing that we are going to see is that OH from our sodium hydroxide is going to pull that proton off and give us an intermediate where we have a negative charge right over here, and then I have the rest of my molecule with the R group over here and a plus like that. I know that it doesn't really look like a typical molecule that we normally are used to seeing, but when it comes to molecules like that, especially when you have a negative charge next to a sulfur, for whatever reason, those things are comparatively stable, and the position between nitrogen and sulfur in thiamine, it is actually fairly acidic, and you can definitely make this not particularly resonance stabilized anionic species without too much trouble. Then what we're going to see here is that this negative charge is going to attack our carbonyl. Aldehydes are wickedly electrophilic, so of course, if we have anything nucleophilic around, we are going to attack those aldehydes. That's going to give you an intermediate where you have your phenyl group, we have carbon, oxygen here, hydrogen, and then I have my thiamine part, which I will draw down there like so. We have whatever that R group is sitting like that. Then we are going to protonate our negatively charged oxygen, so I'm going to use another equivalent of water floating around to make that happen. So that will give me the species that looks like that. So I have my OH here, hydrogen, and then again I have my thiamine part with whatever that R group is sitting over here. Then, because we have this positively charged moiety and the oxygen sitting on the same carbon, the hydrogen that we have over here is actually fairly acidic, so we can rather easily deprotonate that in our basic conditions. So what we're going to see is that our base, our OH minus, is going to come in, pull that proton off, and we are going to form the following species, which as soon as I draw it, you will see something rather interesting about that. So we have a double bond here, we have a nitrogen, we've got our sulfur, the rest of the molecule like that. So now what I have here, on one end over here, I have essentially what looks like an enol. On the other hand, over here, I have what looks like an enamine. So in other words, that position is going to be rather nucleophilic. And mainly the nucleophile here is actually going to be our carbon with the OH group, because the enamine is essentially more nucleophilic than an enol. So what we can do here is these electrons go here, these electrons go on the carbon, and we can show a resonance structure with a minus on the carbon. But if we are working in the presence of a carbonyl, like our benzaldehyde, instead what we can do is just essentially a direct attack on our carbonyl, like so, which in this case going to give us the following intermediate. We have COH over here. I've got a new carbon-carbon bond with the O minus, the phenyl group over there. Then we have our nitrogen and sulfur over here, and whatever that R group is. So we have this rather interesting looking intermediate. Now we can have an easy intramolecular proton transfer over here, which going to give me a very similar looking intermediate, but now my oxygen is on the left side, is negatively charged. So I have OH here, I've got my phenyl group, this hydrogen that I had here is still there, I have my nitrogen containing piece, and then I have the rest of my molecule. And now we can kick our thiamine group out by essentially doing this, which going to give us our final product with the phenyl group, CO double bond, COH, phenyl group, hydrogen over here, and our catalyst, which can go into the next cycle of this reaction and catalyze the next reaction together. So let's put it all on the screen like that. So we can do that, and that essentially brings us the final product. As I've mentioned before, this is essentially a benzyne condensation, but with a slightly fancier reagent, which tends to give a slightly better yield. Typical benzyne condensation can give you the similar product in the presence of the cyanide and many other catalysts. So if you're curious, you guys can always go to my benzyne condensation video and look at that one for the details of this mechanism. Alright, next, moving to the next problem, we have a synthesis. So provide a multi-step synthesis for the described product from the indicated starting material and any inorganic reagent and any organic reagents containing one carbon. Alright, the best answer will require 9 or fewer steps. Well, 9 steps is quite a lot, but okay, let's look at what our final product looks like. Okay, we can deal with that. So let's draw it all together so I can kind of have it on the same page over here, so it's a little bit easier to see. So I have this part, I have my ester over here, and I have this guy over there. Alright, so we have our starting material and one carbon that I can take from wherever I like. Okay, what I'm seeing here is that this part of the molecule is right over here, and also it is right over here. So the extra carbon that we brought into our system must be this carbon of the carbonyl. Now, looking at my molecule and thinking about that retrosynthetically, my final product here is going to be an ester. So there are multiple different ways how we can make an ester, but probably the easiest one that comes to mind is going to be via Fischer esterification. So in order to get the Fischer esterification going there, we need to have an alcohol, which is going to be this one, and the corresponding carboxylic acid. So our carboxylic acid is going to be this one with a methyl group. So we're going to make both of those starting from our starting material. Now, in order to get the phenol, we cannot easily get the phenol from the aromatic molecule right away, but we can make it via the diazonium salts. So this one is going to come to us from the diazonium salt plus with whatever counter ion, which we can make from the starting material. And the acid that we can get here, probably we're going to make via the Grignard reaction, so that would mean that we would have to have some sort of a bromide, and then this one comes from our starting material as well. So with that in mind, in order to put our entire synthesis all together, I have some space over here, so I'm going to do it here. I'm going to start with my starting material. I'm going to brominate it, so Br2 iron bromide, FeBr, oops, it's FeBr3 of course. We are going to end up with the bromide here and in the ortho position as well, but we will pretend that we can easily separate those two molecules. Then we are going to treat that with magnesium, that's going to give us our Grignard reagent, so magnesium bromide over here. Then we are going to treat that with CO2 and then do the acidic workup, so that gives us our carboxylic acid over here, so we have COOH like that. Now, in order to make our phenol, we are going to start with the toluene again, but now our first step is going to be nitration, so it's going to be HNO3 and H2SO4. That would give us a nitro group in the para position over here. Then we are going to do the reduction reaction, so something like iron in acid or plenty of other ways how you can do it. So we are going to end up with the corresponding NH2 over here, assuming the workup to neutralize and all of that fun stuff. Then we are going to treat that with sodium NaNO2, so sodium nitrite in the presence of HCl and 0 degrees. That is going to give us the diazonium compound, so we'll have N2 plus, and in this case Cl minus is going to be our counter ion for that one. And in order to bring that to an alcohol, to a phenol, we are just going to treat that with water, or water in the presence of sodium hydroxide. Sometimes you can also see the presence of the copper oxide, copper 1 oxide, so Cu2O. All of those will work for our purposes to make the phenol over here like that. And then finally we are going to take our carboxylic acid, our phenol, and we will react both of those with each other via simple Fischer esterification to give us our final product like that. And to do the Fischer esterification, we just mix those two things together, add strong acid as a catalyst, and we're done. Okay. So the next one that we have another synthesis, so starting from this guy and any compounds containing 3 or fewer carbons, we need to make that. Okay, let's figure that out. So I'm going to draw that thing over here. So this, what else did I have there? Okay, so we have a double bond here, we've got these two and NH2 like so. Okay, so where my starting material maps onto this monstrosity? Well, a very good question. Probably my starting material, which is this part, looks like it is over here. So that means that I'm going to be adding a couple of carbons here, something over there to make this amine, and looks like I'm going to be adding a couple of carbons over there as well. Interesting. Very, very interesting. So let's break it down retrosynthetically and think how we can make different functional groups. So the primary amine over here with an extra carbon onto it is probably the result of the nitrile reduction. So that one is going to be coming from the nitrile. Then the double bond that I have over here, the most effective way to make a double bond is via the Wittig reaction, so probably we're going to be using Wittig to get that one, which means that our predecessor, our intermediate here, must have been something of that sort. So we have the carbonyl over here, which we're going to convert into a double bond via Wittig, and we have a nitrile over there, which we can reduce to make our primary amine. To get this nitrile, what I'm seeing here, we have the alpha and beta, so this is a beta position, so that means I could potentially get that nitrile onto my molecule via the conjugate addition. So if I had a double bond over here, then I can add the nitrile via the conjugate addition. Now, in order to make this double bond, this is an alpha beta unsaturated compound, so we can make that one via the intramolecular aldol condensation, so that would be something of this sort. So I have this part, carbonyl here, and then that would be another carbonyl there like that, and then from here I am going to have to make a bond between these two guys, and that probably is going to be some sort of alpha substitution. So if I have an enolate, something of this sort, and then I react that with the carbonyl with the so it's two carbons, so a leaving group over here, so probably something of that sort. Now, if I have an enolate and I try to react it with a carbonyl like that, the problem that I'm going to end up with is that aldehydes are extremely electrophilic as well, so I'm going to have a bunch of co-products, so that's probably not the best idea. But what if instead of my carbonyl I had a protecting group on that? So what if instead of that guy I'll use instead something like this, an acetal, and then I can take protection off and do the intramolecular reaction, and in order to get that guy I can use 3 carbons of yours, so I can make that. Okay, so looks like we have a synthesis kind of panning itself out, so let's put it all together. So I am going to start by taking this guy over here, and I'm going to react that with ethylene glycol in the presence of acid to put essentially a protecting group on my carbonyl like so. So I have this guy over here. Since I can only use molecules with 3 carbons or fewer, this one has 4 carbons, so unfortunately I cannot start from that from the very beginning, but my starting material here contains 2 carbons and starting material here contains 2 carbons, so I can assemble this guy. Then I'm going to take the carbonyl that I have, and since I need to do the alpha substitution at this position, this is a more substituted place, I'm going to use something like sodium hydride, a slow-acting base that's going to give me a thermodynamic 100% enolization here, and then I'm going to react these two guys with each other to make a product that will look like this. Then I'm going to kill 2 birds with the same stone by taking the protecting group off, so I'm going to have H plus a little bit of water, and I'm going to increase the temperature here, so once my protecting group pops off, I can do the aldol condensation in acidic media, which is going to give me my alpha-beta unsaturated compound. Then I will react it with something like a sodium cyanide, so sodium cyanide or potassium cyanide, to get the and we probably need some sort of a product solvent here, so let's say we'll do that in methanol to get my conjugate 1,4 addition. Then in order to add the double bond on, I'm going to do Wittig reaction, so that's going to be PBH3, the enolate, the E-lead that looks like that, which we can make from the corresponding ethyl bromide and triphenylphosphine. Triphenylphosphine is not going to end up as the part of my final product, so I don't think that the limitation of 3 carbons works for that one. And then in order to do our reduction of the nitrile, we are going to use something like lithium aluminum hydride, and then we are going to do our acidic workup, and we have our final products. Yeah, that one is a rather interesting one. I would say it's a very creative one. But, you can still put it together. Anyways, let's move on to the next question. And for the next one, surprise, surprise, we have another synthesis. So for this synthesis over here, we are starting with a simple cyclohexane, and we are making that dude over there. Okay. Yeah, that actually seems relatively manageable. Let's draw this guy out. So I have this part, I had 1 oxygen, 2nd oxygen, the acetal and cyclohexene ring over there like so. Okay, so in this case we can use 2 carbons or fewer to accomplish this synthesis. So the first thing that's sort of like staring at me right away is that we have the acetal over here as our functional group, which means that the predecessor is going to be the corresponding alcohol with 1 OH looking at us, 1 OH looking away from us, and the other part is going to be our ketone, which is going to look like that. Synthesis of the diol is going to be trivial. We are going to start with our starting material, and that is just a dihydroxylation that gives you a trans diol like that. So step number 1 is going to be MCP BA, and step number 2 is going to be opening of that epoxide intermediate in either acidic or basic conditions, so that part is irrelevant how exactly you do that. That is just a standard reaction right out of the textbook. Now, in order to make our ketone on the right side, well, that part is going to be a little bit trickier. Normally, what we are going to get for ketones, the way we are synthesizing ketones, is via the oxidation of an alcohol. So if my predecessor here is going to be a corresponding alcohol, it would look something like this. Then we make alcohols via the Grignard reaction, so we are going to be making this bond over here, which means that the predecessor to that guy is going to be the corresponding Grignard reagent magnesium bromide over here, and acetaldehyde, and we can easily make our Grignard reagent from our starting material. So for that one, we are going to start with the starting material. Step number 1 is going to be HBr, just a regular textbook hydrohalogenation. Step number 2 is going to be reaction with our magnesium in the presence of the THF as our solvent, or dry ether if you like. Then we are reacting it with our acetaldehyde, and then we are going to do the aqueous workup. After that, we are going to do the oxidation, and for that one, since this is a secondary alcohol, it doesn't matter how you're going to do your oxidation. You can do it via the Jones reagent, Swern, PCC, DMP, you name it. Let's say we are going to use PCC over here, because why not? And then finally, in order to make our acetal, we are just going to use acid as a catalyst, mix our diol and a ketone, and we got it. So this one was actually quite easy. Alright, cool. Let's move on to the last page of this exam. And for the last page, we are starting with the cyclobutene. Okay. And we can use 4 or fewer carbons for our other compounds, and we are making that. Huh. Okay, that's interesting. Well, let's draw it here. So I have a 5-membered ring, so I have a couple of nitriles there. So I have a CN over here, I have a CN over there, then I have a, where do I have a, okay, the double bond, have a double bond methyl group, and then we have a carbonyl over here like that. Okay, so it is really not obvious how we are going to be making this compound, so let's brainstorm. We have a couple of nitriles here. Adding 2 nitriles here and making sure that they are on the same side, that is an interesting challenge, so probably we are going to see some sort of a very stereoselective reaction somewhere in the middle here. What exactly it's going to be? Well, I don't know yet, we'll see. One thing that kind of jumps at me right away, though, that we have this alpha-beta unsaturated compound over here with a double bond, so we are likely going to make that via the aldol condensation. So if we dig through the aldol condensation predecessor here, and we think how our predecessor would look like, well, I would have cyanide number 1, cyanide number 2 over here, then I have carbon, carbon, carbonyl over here, carbon, carbon, and another carbonyl over there. Okay, and I think I see where we're going with that. So, the bond that we are making via the aldol condensations between these 2 carbons. So we have a carbon over here, we have a carbon over here, the alpha position we are going to enolize that, and we're just doing our aldol condensation over here. So that is just going to be something like sodium ethoxide, a little bit of heat, and we get our product. Now, this is a very symmetrical dicarbonyl, and we can get that guy via the ozonolysis. If we had a double bond right over here, and then I have cyanide over there and another cyanide over here. So during the ozonolysis, we cut through this double bond, which means that our steps for these reactions are going to be step number 1, O3, step number 2, that is something like dimethyl sulfide or whatever else we want to use in this case. And the reason why I say that now I see where we're going with that, because look at that, guys. We have a 6-membered ring, which has a double bond and a couple of electron withdrawing groups right next to it. This is the product of the Diels-Alder reaction. So in our Diels-Alder reaction, we ended up making this bond here and that bond here. So this part used to be our dienophile, and the left side over here used to be our diene, which means that the predecessor here used to be this guy and a cyanide or a nitrile that looks like that. So for our Diels-Alder reaction, this goes here, that goes there, and that gives us our intermediate. And also look at this. We have 1, 2, 3, 4 carbons, so we can use 4 carbons or less for our starting material, and our nitrile that we need to use for our Diels-Alder reaction is 4-carbon compound. So we have our reagent and we don't need to synthesize it in any way or form. That makes it a little bit easier. Now, the problem that we have here is how in the world we're going to make this guy from our starting material. And the reason why I kind of raised the brow at my starting material is because cyclobutene like that is actually quite unstable. Those guys are not very thermally stable and they will tend to burst open when we heat them. And if we heat it up a little bit, essentially what we are going to see is a reaction like this, where this going to get us literally our starting material for the Diels-Alder reaction. So that is a pericyclic reaction, that is an electrocyclic ring opening that can be catalyzed by either heat or actually light. In this case, it really doesn't matter how you do it, but that bursts open and gives us our diene. So although this synthesis looks incredibly difficult, it actually turns out to be quite easy as soon as we realize that the Diels-Alder is the important part here and the molecule is, being cut open via the azanolysis, and then we close it up. So sometimes it might not be obvious where exactly you need to go with your synthesis, so don't be afraid to brainstorming. And since this was the last question in this exam, we are finally done. So didn't take us quite 3 hours, but took us over 2 hours to get through all this stuff. So hopefully you're still here with me, and if you are, thank you for watching till the very end. If you like this format of the videos where I can take exams from different institutions and basically do this semi-live where I go through this exam and solve it with you, explaining why the answers are what they're supposed to be, let me know in the comments below, and if you have a practice test from your instructor, maybe I can look at that as well. You can always submit your questions on my website, so if you go to Organic Chemistry Tutor and scroll down, after all of my tutorials and whatnot, there is a form where you can submit your questions, and if you have a practice test that you are interested in having me go over that practice test, you can always submit it here, and I might as well choose that for one of the videos and go through that as well. So hopefully you guys liked this video and learned something new from that. And if you did, hit the like button, subscribe to the channel for regular organic chemistry updates and tutorials, check out this video next, and I will see you next time.